what is light? You know, for a long time it was thought the answer is obvious. Light is made up of waves, electromagnetic waves, undulating electric and magnetic forces travelling through space, much like waves on the surface of a liquid. Okay. This seemed obvious for a number of reasons. For example, when waves pass through a narrow gap in a barrier, they spread out somewhat to the side rather than going straight on. And that's what light does. Put two gaps close together, and the humps and troughs from the two gaps overlap and interfere with each other. This gives rise to directions where the humps and troughs are in step and they reinforce each other. And then in between, the humps and troughs are out of step, they cancel each other out, and you get very little activity. Now this is exactly the kind of behavior we get with light. Pass light through two parallel slits and we get bright beams going off in a number of directions with little in between. And this is not what you'd expect if light were made up of particles, such as this. The tiny droplets of liquid you get from a spray can, for example. Okay, I can demonstrate this like this. Actually, this is going to get a bit messy. No, I'll leave it to my lab assistant to do it outside. Okay, that's what you get with particles. Just two bands, one for each of the slits. So the fact that there are more than two bands here demonstrates quite conclusively that light is made up of waves. Except, if you examine closely how light gives up its energy when it hits the screen using a very weak beam, all you see at first are tiny dots. Not the smoothed out distribution you might expect if light were a gently undulating wave. As more and more light arrives on the screen, so you get more dots and the interference pattern begins to emerge. But note, the energy is being given up as localized dots. It's as though the screen had been hit by a hail of gunfire, a hail of tiny particles. We call these tiny bundles of energy photons. So, what is light? Waves or particles? The fact that there are more than two patches of light can only be described in terms of light being made up of waves. But the fact that the light arrives and gives up energy as dots can only be explained by saying light is particles. So the crucial question becomes, how can something be both a wave, spread out over space with a succession of humps and troughs, and at the same time not spread out, a tiny localized point-like particle? This dilemma is known as the wave-particle paradox. This behavior isn't confined to light. What about matter? What is matter? Well, all the objects we see about us are made up of atoms, and atoms are made up of a nucleus surrounded by electrons. The nucleus is made up of neutrons and protons. So it seems pretty clear that we're dealing with particles. Take a beam of electrons like the ones you get in the older style TVs and computer monitors. The electrons are emitted from an electron gun at the back of the tube. and then they travel to the screen where they hit the screen here. There they give up their energy that gets converted into the light that makes up the picture that we see. They hit the screen like a hail of tiny bullets. Fair enough, no, that's what we expect if electrons are tiny particles. The trouble is that while they're traveling from the gun to the screen, they behave like waves. Pass them through two slits in a barrier, and we get this on the screen. An interference pattern, just as we got with light, a whole series of patches and nothing in between. And all this has to be due to the overlapping of humps and troughs. And this shows how those interference fringes are successively built up from individual electron impacts. It looks exactly what we had for light. And what's more, it's not just electrons. The other constituents of matter, protons, they also exhibit wave-particle duality. Even beams of complete atoms or complete molecules. Everything is afflicted by wave-particle duality. So, what are we to make of it all? Well, back in the 1920s, the Danish physicist Niels Bohr, he came up with a challenging suggestion. He declared that we are to stop asking questions of the sort, what is light? What is an electron? We have to redefine the question itself. Instead, we are to talk only of observed behavior. How are things observed to behave? So, for example, take the case of the electron in the TV tube. We can ask how the electron moves through space, and hence where exactly to find it on the screen. Answer, it is observed to move through space like a wave. Or alternatively, we can ask how it interacts when it gets to the screen. How does it give up its energy? Answer, we observe it to give up its energy as dots, tiny particles. Either we're asking how it moves through space or how it interacts when it gets to its destination. We can't be asking both questions at the same time. So, there's never any call to have to use the concepts wave and particle at the same time. Depending on what type of observation we're talking about, it's one or the other. It's never both. Hence, the wave-particle paradox is solved, according to Bohr. But the solution comes at a price. The price is we're not allowed to ask questions of light or of anything else outside of the context of us observing the light or observing the electron or whatever. Such questions are meaningless. Suppose, for example, out there in empty space there's an electron on its own, not being observed, not interacting with anything. Under those circumstances, what is it? Is it a wave or is it a particle? No, you can't ask that question. It's meaningless. The very words wave, particle, electron even, they're all words used specifically to describe observations. It's a misuse of language to try and use those same words to describe what might exist in between the observations. In effect, what Bohr was saying is that we used to believe the job of the scientist was to describe the world as it is. Okay, and in order to do that, you have to look at it through a microscope, say, on the small scale, or the telescope on the large scale. You have to experiment on it. But having done all that, having observed it, what you eventually write down in your science textbook is a description of the world, whether or not you're still looking at it. But what Bohr says is, no. What you've written down here is a description of you looking at the world, what it's like to interact with the world. It's not about the world as it might be in itself. You've said nothing about that, and never will. The German physicist Werner Heisenberg backed up Bohr and declared, "It is possible to ask whether there is still concealed behind the statistical universe of perception a true universe in which the law of causality would be valid. But such speculation seems to us to be without value and meaningless. For physics must confine itself to the description of the relationship between perceptions." The relationship between perceptions, the relationship between observations. We can't say anything about the world in itself, a world that is not being observed. What a shocking idea. Not surprisingly, not everyone goes along with it. Einstein, in his discussions with Bohr, for instance, Einstein maintained to his dying day that the goal of science remains what we always assumed it was, the description of an objective world out there, independent of whether we happen to be observing it. But it has to be said that 80 years of fruitless argument, and we're still no closer to realizing Einstein's dream today than he was then. And with each succeeding year, it could be argued that it looks more and more as though Bohr was right. We really are up against the barrier of the knowable. Tony, I was just wondering, I've been saying how when not being observed, it becomes meaningless, okay? Well, I was wondering where I ought to add a bit, because the viewer might be thinking that once they stop viewing the program and I'm not being observed, I suddenly become, meaningless, or don't you think they're bothered, or what?
Do you know what, Russell? I really don't think they're bothered what's happening to you when they're not watching the program. Sorry.
Thank you. Well, I'm bothered. In fact, I think tonight I ought to sort of stay awake and keep observing myself. In fact, that is probably why my dreams don't make sense. They're meaningless because I'm not being observed. I bet Freud never thought about that.
Next series then.